Hello everyone, my name is Arik Senderovic. I'm an assistant professor at the University of Toronto, as the CN Tower here shows. Today I will talk to you about automated mining of simulation models using event data. This is a joint work with Ofer Baron, also from the University of Toronto, and Galit Yom Tov from the Technion. In this work, we're motivated by congested emergency department systems. We see on the left-hand side an emergency department in Israel during a mass casualty event drill. And on the right-hand side, we see an emergency department congested to the extreme in China. And what we want to do is we want to run some analysis in those systems in order to be able to eventually improve them and lessen the congestion. The approach we're going to take in this work is based on queue mining, which is a relatively new research area introduced in 2014. It is an area that sits on the intersection between data-driven analytics, machine learning, data mining, process mining, and operations management, specifically queuing theory and scheduling. We start by looking at the congested system, and we assume that everything that is performed in the system, or most of the activities, are logged and stored in databases. And queue mining is about taking these databases, apply data-driven analytics, data mining, for instance, in order to elicit a queuing model that can then be used for simulation or for exact queuing-based analysis. Here's an example for an animation that was created using an emergency department data coming from the C-Lab, the Service Enterprise Engineering Laboratory at the Technion, that is now managed by Galit Yom Tov. This is data from a Singapore emergency department. Patients are all arriving in the beginning and go into triage, and then there's a complex network of activities that these patients encounter. Now, in this data, we do not observe resources, and we do not know when patients are queuing and when they're actually in service. All we know is when some of these activities start and end, but we do not know which events correspond to queuing. What you see in front of you is real data. It's what we call trace-based simulation. There's nothing stochastic here. This is a playout of the sample path that actually took place in October 2012, specifically October 1st, 2012, at 3 a.m. in the morning right now. We see the different patients. We see some of them splitting and joining and routing through the different activities. And these are the ideas that we're going to use in order to construct a simulation model of the system. So how does queue mining work? Queue mining starts by learning the building blocks of the queuing network. Its structure, as you saw before, meaning its routing. For example, if it's Markovian routing, then learning its transition metrics, the dynamics of the system, i.e. the arrival process, the service times, the connections between the relationship between arrivals and service times, and so on, the scheduling policies, how am I prioritizing my patients, and so on. And then once the model is obtained, let's say this is the model of the emergency department, we can use closed form expressions from queuing theory or simulation in order to conduct the analysis that we have in mind. Now, in today's talk, we will focus on prescriptive analytics using queue mining. That is, we will try to improve prioritization of patients. We'll try to improve the routing and the staffing decisions in our process. We will not talk about descriptive analytics or predictive analytics, which are also important and play an important role in the queue mining literature. Having given you the motivation and the background for our work, I would like to focus on the specific task that we have at hand. We would like to mine automatically with a press of a button, a simulation model from event data collected by our emergency department. However, we're going to encounter the problem of missing information. So some of the information that we usually assume to exist in queue mining will not be apparent in our log. And we will show you an approach that we also implement in a tool for doing exactly that, mining a simulation model. I will then arrive at some challenges, conclusions, and talk about future work. To start with related work, simulation mining, it was a hot topic in the area of process and data mining in 2009, when Rosinat et al. Proposed a model to mine, proposed a method to mine Petri nets from event data. And then in 2018, In our previous work, we've shown an approach to mine detailed simulation models that can then be abstracted and simplified into collapsed queuing networks and analyzed appropriately. The idea is that we automatically mine these queuing and other process models, and then we use simulation for prescriptive analytics to set the number of resources they need and so on. And this method usually assumes some knowledge about the resources and the queuing events in the system. However, as I hinted before, when I've shown you the trace-based simulator of the emergency department, this kind of information is not always available. What is typically available? This is an emergency department data set, very typical, and we will claim that it has some missing information. What we have is typically a visit ID or a patient ID, and the patient goes through different steps or through different activities in the process of being treated: reception, triage, treatment, and so on. And to each of these activities, we typically have a single timestamp attached. It can be a start, which is what we're going to assume in this work. It's the start of reception, start of triage, start of treatment, or it can be the end. But usually the queuing for reception, the queuing for triage, and the queuing for treatment, we don't know when it starts and when it ends. We simply know that the patient has now arrived to the next station or the next activity of treatment. Now, another piece of information is the resource that we usually in queue mining assume to have in the data. For example, reception is performed by the receptionist, triage is performed by the nurse, treatment is performed by the physician. In this work, we're going to assume that this column is missing because essentially from all the emergency department data sets that we encountered in our work, in our experience, we do not have resource information, and the time stamp that is associated with activity is only the start time or the end time for that station. We do not have the full temporal information. So the only thing we're going to assume to have are these three attributes: case identifier, the activity, and the time in which this activity actually occurred. And so with this in mind, we wish to close the following gap. We want to mine a queuing model or a simulation model, assuming to have only the visit ID, the activity, and the time, which is the usual case in most emergency departments that we encounter. And the research question is, how do we create a reasonable model of the system, of the underlying reality? For example, in our emergency department, how do we create a suitable model automatically? And I'll show you what it takes to do so. Specifically, we would like to have a scalable solution that would run quickly on any given new emergency department data and would not be tailored to a single emergency department. And so we see that these three fields that we discussed before are very common in most emergency departments that we have encountered. Therefore, we claim that the solution is pretty much robust. So our solution is based on mining an infinite server model, more specifically, a state-dependent activity network that would approximate congestion. It would not represent congestion directly by having queues in our model. Our nodes in that network are activities that appear in the emergency department data. We do not assume any resource information. And the time that patients stay in each of the nodes is the time between two consecutive start times or two consecutive end times. For example, if a patient arrives into triage, we assume that the patient stays in triage until they start the next station, which is treatment. And what remains to be fitted in this model are the durations for the activities, how long patients stay in each of the durations. We feed the densities, and we'll see that this can be extended to state-dependent densities. So the more patients we have in a certain station or activity, the longer, for instance, the duration is going to be. So essentially, we will condition on the state of the system. We need to model exogenous arrivals and fit their arrival rate. And we need to fit a Markovian routing matrix, and I'm going to discuss a little bit how this Markovian assumption can be relaxed and patient routing can be captured a bit different. Now, the model, I'm not going to go too much into the details, but we have a higher level black box queuing model that is an MTG infinity model. We have inhomogeneous Poisson arrivals. The time spent in the system behaves according to a general distribution that is state dependent. I'm going to specify what it is. The G is essentially a lower level processing network or activity network that we need to also feed from the data. So in order to feed the high level model, since we have an infinite server model, it's enough only to feed the arrival process, and the G is essentially a low level processing network that we also feed from the data, as I said. The network has the set of activities, A, set of arcs that can change over time, which is basically the routing metrics. And we have densities of durations of how long patients spend in the different arcs, on the different arcs or on the different activities. It depends. We actually have both models where patients spend time in nodes and when patients spend time on the arcs. But for our example, let's assume that we only spend time in the nodes. We can essentially use our model to feed a state-dependent density to each of the activities. And that's what we're going to do. So a bit about the implementation. Basically, our current algorithm or approach takes trace data or event data, as I told you before, with missing information, and takes certain hyperparameters. For example, noise filtering, because we may want to filter some of the infrequent activities. We have additional hyperparameters that I do not have time to go into their details. And we're performing a basic model fitting. This is a step one model fitting. We learn the topology of the network. We fit the arrival process. We fit a Markovian transition function that tells us how the patients are routed between the different nodes. We fit sojourn time distributions to each of the activities. And this is our very basic model. This is already implemented. Whatever is in blue was already implemented for this project. Then we also cluster arrivals together and cluster the number of patients in the system and try two additional alternative models. In one of them, we fit sojourn times to be conditioned on the number of arrivals, let's say per hour in a certain time window. In another model, we try to condition those sojourn times on the different clusters of the number of patients in the system. And I will talk a little bit about why we do clustering instead of just conditioning on the absolute number in the system. And essentially the problem there is underfitting. An additional alternative that we proposed was to have the routing instead of Markovian be path dependent, meaning that if my path is similar to other patients who went through similar paths, I'm going to use their historical paths to predict my next activity in a fashion that is similar to k-nearest neighbors algorithm. So basically using machine learning, trying to improve the transition function. In addition, we implemented an arrival prediction module that is based on LSTM neural networks. We have additional components that we did not fully implement yet, a multi-class component that takes into a multi-class model alternative that takes into account the fact that patients come with different triage scores, a capacity inference engine that tries to infer the number of resources, a hyperparameter selection module, a counterfactual analysis module that is based on machine learning, and so on and so forth. Now, the way we validated our model, we essentially used our implementation, our tool that was developed based on our algorithms to create such an activity network and then compare the resulting, for instance, total number of patients in the system to the actual number of patients in the system. And we did this for 2 hospitals, 2 emergency departments, and we also went outside of the domain of emergency departments and fitted to 2 cloud service data sets and actually had some partial success there as well. To demonstrate one system, this is again C data, essentially data that comes from the C lab at the Technion. This is Carmel Hospital in Israel. And here we're trying to simulate more than 7,000 hours in that hospital and compare that to the actual realization. So the actual realization is in blue, denoted by real. The mean is in red, the mean of the simulator. We run it for 30 times. And the confidence interval for 30 runs is denoted by green. Now you cannot see the picture very well. I'm going to zoom in. The y-axis are the counts of how many total patients we have in the system, and the x-axis are time in hours. When we zoom in, we see that the blue line, the real number of patients in the system, is typically well within our confidence intervals, and the mean is a good replication of that real function. Going to the specific activities, so this was the total number of patients in the hospital. We see that for the reception activity, which is a very common and upstream activity, we still have some success in replicating the actual realizations. While for more rare and downstream activities like consultancy and external examinations, we have partial success, partly because of underfitting. We don't have enough information in our data to cover the exact densities of these activities. What are the challenges in Q mining and in these simulation mining models? First of all, what is the proper evaluation? How do we evaluate our simulation model? Is looking at the total number of patients in the system and the length of stay of these patients and comparing them between the simulated and the real. would that be enough, or do we need to run more tests? And the answer is yes, we need to perform further analysis in order to improve our measure of fit, or measure of goodness of fit between the simulated model and the data. The second thing is that we want to prove that our state-dependent activity networks are somewhat a good representation of the actual congestion that we see in the emergency department. And to this end, we're working on some theoretical equivalences between our model that we propose in the paper and processor sharing queues. In addition, to avoid underfitting and overfitting, we're doing clustering to avoid underfitting when in situations where we don't have enough data. And we use all kinds of abstraction mechanisms to filter activities, filter parameters, and aggregate some activities together, essentially to reduce the number of parameters we're using in the mining process. And that avoids overfitting. To conclude, I've presented a method for automated mining of simulation models from event data with missing information. In the working paper, we see optimistic results for 4 real-world data sets, 2 of which are emergency department data sets. And as future work, we're going to try and implement the method in a live project that we have with the Toronto Hospital, where we're actually going to try and recommend certain changes in the process and in the system that would come out of our simulation. And then we will be able to use the data, the fresh data, to track whether these changes were helpful or not. We also want to extend the framework with additional features. As you saw, not all of our features were implemented yet. We want to continue and implement the orange features on that chart. And we would like to add theoretical guarantees on the equivalence of our models to with congestion-aware models. Thank you very much, and I'll be happy to take your questions during the discussion period. Thank you.